Hey guys, welcome to another video. So today we continue the journey on the integration with recurrence topic as part of the extension 2 4-unit syllabus. If you haven't already done so, please hit up the video, the first video in the series where I lay down the framework for doing integration with recurrence questions. In particular, most of the questions use integration by parts, where we start talking about, or start using the acronym LI8, which is a really good acronym used to find the function of u, right, which is the one you differentiate, and dv is the one you integrate. Now, I also mentioned last week, and this is quite crucial for this week, where this week we're going to deal with integration with recurrence. Last week I said, also the last lesson I said, integration by parts is usually the one, usually the process we use, and that's the same with today. And I sort of mentioned or sort of alluded to where situations where LI8 fails. And by that, today you'll see a number of questions relating to trigonometry where LI8 really doesn't do it. So then you got to go back to first principles of the LI8. And LI8, the principle is you have that acronym LIATE, which basically says to you, these are the functions in that particular order that you can differentiate, right? But what's more important and what your teacher really should tell you is that the whole purpose of LI8 is to pick actually the function that you can integrate, right? That's really the one that you need to do. You want to pick the easier function to integrate. For example, log is really hard to integrate. So that's why we choose it to differentiate, right? First. Exponentials in the last letter in LI8, really easy to integrate. So therefore, it's the last function we use to differentiate. So LI8 is just a mechanism for you to choose in order of difficulty what you can't integrate, right? So I'll talk about that when we do today's lesson. So let's start. Integration with recurrence. Now, I'll keep spelling that with an A in my classes, so let's make sure I spell it right. So I guess before we begin, just because we're dealing with trig today, just to make sure things like if I integrated cos x, right? We all know that that's sine x plus c, integral of sine x dx equals a negative cos x plus c. I think I was told by a student once as a good memory of whether sine integrates or cos integrates negative, the acronym of sine, that is sine integrates negative, right? It's a really neat way of remembering that sin, right? Pretty neat. Helps you remember. So if that works for you, good. If not, that's fine as well. Now, guys, there was one more trig integral that's normally given as part of the reference paper, and that's sec squared, right? So need to remember that sec squared equals a tan x plus c. Now, they're the most common ones. And later on, you might see one with cot as well, but we'll have to derive that in question. So, all right, so let's start doing some of these questions, explore some of the past papers with integration recurrence with trigonometry. Let's go there. So first question from Hills Grammar. Now, when it comes to trig, it can't be more classical. There are two areas, two types of questions, right? So two buckets of questions is probably the best way to do it. There's sine and cos, and there's sec and tan. Sine and cos, sec and tan, they go sort of hand in hand, right? And the reason why I want to distinguish those two is because the approach you take for both of them is the same. Sine and cos has the same approach. Sec and tan have the same approach, right? Let's start with cos. So what's really important for you to identify when you do this guy over here, and I'll box this guy in a blue box. I think I did the same in the last video. That's my integral, my recurrence statement. First part, I need to prove a recurrence statement. So the blue box is my integral, the green is my integration recurrence statement. Write that after proof for n greater than 2, cool. And then you can see in the second part there for 2 marks, that is my value that I have to find once I prove the integral statement, and power 6 looks like that's I6, right? All right, feels like the question is quite straightforward. Prove that recurrence statement, use that recurrence statement. So let's start with the first part. So part 1. So if in equals to the integral with the limits of pi on 2 cos to the power of n x dx. Now, guys, this is the crux of today's lesson. You look at that, and using Lie8, right? Lie8 fails in that there is only one. I say fails. We did this last week, and he sort of passed. That's trig. Last week, we tried to explore maybe if there was just ln and there was nothing else, we put 1 and that was algebra. Now, if you went down this route, you will realize that you couldn't prove the recurrence statement. That is not how you approach this question, unfortunately. So with this type of question, the general rules of Lie8 really does fail. Guys, this is the plan, right? Remember what I said to you. What's the point of Lie8? The point of Lie8 is to actually identify the function that you can integrate, not differentiate, even though that's where Lie8 is helping you sort of define the function of. Lie8 actually tells you in an opposite sort of way what function you need to integrate. So, guys, when you look at the function of cos to the power of n, right? In this case, we're going to split the function into 2 parts, where I'm going to take out 1 power of cos and leave cos to the power of n minus 1x multiplied by cos x dx. Now, why did I do that? Because I know by stripping out cos, I'm going to let this guy be dv. I can integrate cos, right? I did it in the last page. Integral of cos is sine. And then I'm going to apply u to this guy and differentiate this guy. Yeah, and that sort of gets me to, I know I'm on the right path, because when I differentiate this, becomes, the n minus 1 comes down and that becomes n minus 2. You can sort of see in the recurrence there that in minus 2 sort of feels right? I need almost 2 powers down. So I split it up, let it be n minus 1. And when I differentiate, it sort of gives me n minus 2. Also, what's really crucial, and I guess you learn this through practice, is I can integrate that. That is the key. And later on, when we do a sec one, you do exactly the same, right? You do exactly the same, and I'll talk about that later. But for now, guys, let's apply off to the side and do by parts. So let pink, let u equal to cos n minus 1x. So differentiate that. So du equals to, bring down the minus 1, apply the chain rule here, minus 2x multiplied by derivative of, now derivative of cos is negative, right? So negative sine x. So just to clean it up, it'll be negative n minus 1 cos, and dx as well, of course. N minus 1x sine x dx. Right, maybe I should put sine first, doesn't matter. And by the same token here, dv equals to cos x dx, integrate that, becomes positive sine x. Beautiful. All right, got my tools. Yeah, therefore, in using by parts, uv, so cos n minus 1x sine x with the limits of that and that. Now, if I was to I need the integral of this guy, right, times this guy. So I'm pulling out the constants, which is that guy outside, so it'll be plus n minus 1 integral between the limits of that. This function times this now, sine times sine, sine squared, so it'll be cos. I didn't have enough horizontal space, so bear with me. Ooh, I'm on the edge. Going to move this one down here. Actually, you know what? Do this, move it up there, move this guy up here as well. I just need a little bit of horizontal space, that's all. Okay, cool. So it's so because n minus 1x, oh sorry, n minus 2, right? Because it's derivative. Guys, I didn't differentiate that properly, so when the power comes down, that becomes 2. Good, that's what I said, that's what I need it to do. So let me get rid of this. Make that a 2. X and then sine squared. Great, I'm on the right track. Now, once you got 2 steps now. One, to basically sub in the limits, right, of pi on 2 and 0 into here. Now, without doing too much work, I know that cos pi on 2 is 0 and sine 0 is 0. So both of these terms will be 0. This whole thing zeroizes out, right? Perfect. Good, because in the thing I have to prove, you can see there is no term in front. So I'm expecting the limits here to sort of neutralize this expression. Now, on this side, guys, what am I trying to do? I'm trying to get this expression here, right? This expression here to look like the original integral of cos to the power of n, right? So then I can replace it with i's, right? So, and the way you do it is use the identity that sine squared is equal to 1 minus cos squared, right? That's how we're going to play this. So let's see, this becomes n minus 1 outside of the limit pi on 2. That's like cos n minus 2x, 1 minus cos squared. And then hopefully you can see what we're going to do here. We're just going to expand this, right? Times that, and you sort of get cos n minus 2x minus cos, the 2 fills up the gap, so it becomes cos n, right? Which is in minus 2 minus in, right? So let's see. Let's do the full working out here. Yeah, make your teachers happy. That's like pi on 2. That times 1. That looks exactly the same as the original in, but with n minus 2. That guy fills the gap. It becomes cos nx. Right, guys, in this case then, right, we know that guy is in minus 2. That guy is in. Let's make it clear to you. What I'm going to do then is sub in those i's and then make in the subject to get my recurrence statement. So that guy there, that's in minus 2 minus in. So if I once again expand this, right, I get in. You know what? Let's be big brain. Expand and then move the in over. So it becomes like in here. Factorize 1. When I move this guy over, it'll be plus n minus 1 equals to n minus 1 minus 2. Have a quick look because the 1's going to get out. Is n on the bottom there? Perfect. So the 1's go away. And then you get n times that, divide the n over, and you have your recurrence statement that you desire over n minus 2. Great. Yeah, hopefully that wasn't too bad, guys. Hopefully that wasn't too bad. So that's 4 marks. Yeah, I reckon it's 4 marks because of the initial pink part where you needed to identify to yourself to integrate this guy. You got to split one lot of cos out because that's integratable, right? Now let's finish this off. Put a bullet in it. Now, I6, generally speaking, I6 feels really high, but because if you look at the recurrence, it's going down by 2s, so shouldn't be that bad. So I'm gonna do it over here where I can actually see the question. So part 2. So I know that I6 equals 2. So if I sub in n equals to 6, equals to what? 5 on 6 of n minus 2, which is 4. And then I4 equals to 3 on 4i2. Right, and it says I can sub in 2 for the final number. Ooh. Yep, I can sub in 2 for the final number equals to 1 over 2 I0, and then 0 breaks the loop, right? Here, so let's sub in 0 into the formula, guys. I0 off to the side here, right? Equals to integral of 0 on 2. Cos the power of 0 is just 1 dx, subbing in the limit, so that's just x, right? On 2, 0, so that's just pi on 2. Now, once I get that, remember, I now back solve, right? So I put this guy back into here and then recursively move up the ladder, right? So let's see. Therefore, I2 equals to 1/2 pi on 2, right? Which is pi on 4. guys, that guy there recursively into here, right? So then I4 equals to 3/4 of pi on 4. Is that 3 pi on 16? Last but not least, this guy recursively back into here, and then I6. I think, have I done some maths wrong? Why does it feel like I've done something else? So 3/4 I2 is pi on 2, half times that, 3 on 4 times that. Have I done some maths wrong? Because then when I started in 5, maybe not, 5 on 6, multiplied by, no, that's right. So 3 pi on 16. Sorry, I just had a quick look at the answer. It's because they simplified it. So that guy is 2. And so the answer 5 pi on 32. Amazing. There you go. 2 marks. So the recurrence part, pretty straightforward, just recursive, bit painful, a bit tedious, but there you go, guys. How's that? So cos, bit of a trick to start off with to pick out the bit so you can do by parts. I'm going to show you the same question for sec squared, right? So, sorry, for sec x. So now, oh, sorry, I lie. No, this is the one I want to show you. No, I didn't lie. Just went to the wrong slide. Buckets, it doesn't. Now, I just picked one out, guys. You'll see this question so many times. This one doesn't have limits. So to one extent, it's a bit longer, but to another extent, it's probably easier because you don't have to sub in stuff. But look at the marks, 7 marks. Very common for these type of questions because they're a little bit more intense. Right? So that's my integral, and a bit longer, but not too bad. It's my integration recurrence statement. Okay, let's see for this one. Perfect. Now, I like this one. And then just to be absolutely clear, then the integral here, that looks like your original, but with 6, so that's I6. But what's really important is that it's got limits, right? So hopefully it cleans up quite nicely. Let's have a look. Yeah. Let's have a look. So I'll start with part 1, right? Where my IN is equal to integral of sec nx. All right. Now, just like before, the principle is more important than y8. The principle is I want to break up sec to the power of n so that I have something that's integratable. Yes, you can leave it as sec n and 1 is absolutely integratable. But then when you have 1 and you integrate 1, you get x. You don't want x as a function by itself because then you want to stay with trig, right? So I need to break this guy up, right? And remember, I need to break it up to something that's integratable. And coming back to our very first slide, we know that when it was cos, I need to break up cos, but sec, I need sec squared, right? And that's really key. So in this case, I'm going to break this guy up, take out 2 lots of sec. So I can have sec squared so that I can integrate. Guys, I can't emphasize that enough. That is done like that because I can integrate sec squared. Right? Hopefully that makes sense. And this is u in the by parts formula. So off to the side, let u equal to sec n minus 2x. Now, derivative of this, so this is almost like 1 on cos, right? Yeah. So hopefully we can differentiate sec to the power. So let's see. So du, bring down n minus 2, guys, minus 1 to the power. Now, at this point, I keep reminding my students, sometimes they get a bit nervous and they think they're on the wrong track because n minus 3 is nowhere in the formula. It's fine. The gap gets filled later now. And then that's, and then multiply by. Now, just off to the side, you guys okay, that's sec x derivative. Yeah, that's sec 10, right? Don't know whether that's a thing that people learn at school. Should be multiplied by sec x tan x dx, right? So then you can see there the sec x gets filled up. Now let me make sure that my algebra is solid. Perfect. That equals to n minus 2 sec x tan x. So then that becomes n minus 2x tan x. Brilliant. Dx, right? By the way, the second one, much harder than the cos, just putting it out there, right? dv equals to sec squared dx, integrate both sides, equals to tan x. We know that from the first slide. Perfect. Common tools, right? So let's see. Therefore, in equals to uv. No limits, right? No limits, so it'll be just sec. I'm just looking at the order here, so they write out sec tan, so I'll do the same. Sec n minus 2x tan minus, that's constant, right? So it'll be that times that, so it'll be that, so it'll be n minus 2 integral. This guy times this guy is 10 times 10 now. Absolutely on the right track, right? Because we know with identities, tan squared can be converted into an expression with sec squared, right? So let's replace. Now, last question with the cos, I did two things. I subbed in the limits and I replace. This one has no limits. So I'm just going to replace this with the identity of, what's that? Sec squared minus 1. Nice. Okay, let's do this. Now, this one's a bit longer because in the previous question that zeroized, right? But for now, still here. Yeah, there has been more and more of a trend to do limits for this question, where I think some of the limits give you surds and stuff. That's absolutely fine. If I sub that in, can I ask a favor? I'm going to sub it in and then expand it. So let's just do it all in one step. Save us a little bit of time to get n, right? Because the 2 sort of fills in the gap, and minus sec. And minus 2 with that, guys. Nice. Right? And then I know this guy here looks like my original. That's in. This guy here, yeah, looks like my original. Like that. Yeah, so therefore in equals to sec n minus 2x tan x. Yeah, minus. Now, can I, once again, I'll expand that. So minus 2 in and then plus n minus 2 times I minus 2. Guys, I need to group this guy and this guy, right? So bring it over and factorize. I'm almost there. Let me just make sure the signage is right. Perfect. So when I bring it over, in factorize, it'd be 1 plus n minus 2, which is great. So I can see in the question that it's n minus 1, and that's exactly what it is. So now I'm just on cruise control, right? So automatic landing, let's just take it there. That guy there is n minus 1, right? That time gets rid of that, become minus 1, right? So divide minus 1 to everything. Let me see how they express it. Minus 1, perfect. Therefore, in is 1 on, divide that bracket over to that term, sec n minus 2. Oh, we've got the x. Tan x plus, divide the n minus 1 down here, minus 2, n minus 1, n minus 2, guys. How many marks is that? 4 marks? Amazing. All right, 4 marks. Yeah. Excellent. So hopefully that wasn't too bad. Now we're going to use recurrence. The thing about recurrence is step 1, if they give you the limits, sub it in first so you minimize your statement to something that's shorter and more useful. So in this case, before I do anything, right? So I'm going to repackage the limit, repackage the question with limits. So the limits they gave me was, what was the limits? 0 and pi 4. That's nice for tan, right? 0 is 0 and tan is pi 4. So might give me third. So let's have a look. Sec n minus 2 x tan x. Yeah. Is this right? Let me see. Let me see. Do I sub in? I don't actually think I sub in the limit here. Do I? Because if I sub in the limit here, the cos one might be problematic. Let me see. Sec 6. I'm thinking, guys, that I sub in the limit at the end after I do it, but then it's completely nasty. So let me see. Let's see. N6. I think it's unavoidable. Yeah, I think it's unavoidable. It's fine. Okay, let's do it. So pi on 4. Yeah, because it doesn't actually neutralize, which is not ideal, but hey, we are where we are. So minus 2, n minus 1, I, n minus 2. All right, let's see. So when I sub in pi on 4, I get, let's take this guy out first. Pi on 4 is 1, so just be sec pi on 4. So sec pi on 4. Okay, maybe it's not too bad. So n minus 0, plus n minus 2. So I'm just subbing in the limit to the original recurrence, so I can get a recurrence that's cleaner. So in this case, sec pi 4 is 1 on pi, cos is 1 on pi 2, so that's pi 2. So it'd be like, so it's pi 2, root 2, n minus 2 over n minus 1. Yes, okay, cool. Minus 2. Just to get my recurrence. So this one's a little bit harder because they were a bit tricky. In the recurrence proof, they didn't do limits. And then in the subbing in, they're using limits. So you're just going to work a bit harder to sub in the limits. That's fine. Now let's work it. That's my recurrence statement. Right? That's what I need to sub in the 6 to. Oh, don't have space. I'm just going to copy that. That's okay. Put in the next one. Delete all this jazz. Delete this guy. Start here. Yep. All right. Go here. Perfect. All right. I6. Right, we're here. So I6 equals, so when I sub in 6, that's 4. So that's 4 on top here on 5 plus, yeah, what's that? 6. So that's 4 on 5 again. I4. Great. I4. So 4 will be squared. So that's 2 on 3 plus 2 on 3. Huh. Is that 2 though? I think so. 2 on 3. Just looking at it. Yeah, okay, cool. I2, great. Let's see if I get the same answer. I'm doing it a slightly different way to the answers, but let's go. Now this one here, once again, not a nice question when they don't tell you what n values are different to start with, but let's assume I can sub in 2. So that's 0. So that's 1 on 1. So that's 1 plus 2 is 0. Oh, 0. I can't do this. Yeah, I can't do this. So maybe I2 is the lowest I can go to because the n starts getting negative, right? And I0. Let's just go here, right? So I know I2 equals to integral of sec squared, right? With the limits. Sec squared, that's fine. Because I know that is 10. Which is amazing because the answer is just 1. You know? It's the 1. I'll repopulate this. All right. Let's see if I get the answer. So then I4 equals to 2/3 plus, well, 2/3, 4/3. Okay. Let's see. Moment truth. Moment truth. Therefore, I6 4/5 plus 4/5 times 4/3. Guys, what is that? I don't have a calculator. I actually do. Got one of these virtual ones. 4 on 5. So I'm doing it a different way, so hopefully it works. 16 on 15, please. Oh, perfect. 28, never in doubt, guys. 28 on 15, amazing. Never doubted myself. Yeah. So that was a much more intense question based on sec squared, right? It's not your usual, so it's not the same as cos in that it's a bit more intensive with respect to the integral, but also the question, I thought I'd pick one where you don't have the integral at the start. So you don't have the limits at the start, but you do have it at the end. So that's how you react to it. Guys, I want to do one more with trig. The next one is actually a bit of a hack in that you don't actually use your traditional way of doing your recurrence, right? It's to do with cot. So it's actually the way we approach this question a little bit easier than you use. Let's have a look. Sydney grammar. So there is my integration statement there. Right. In the first one, they don't actually tell you to prove recurrence. They just say prove in. Okay, something one, beautiful. And then the next one, they go, okay, prove this recurrence formula. But the way we're going to approach this is slightly different. When they give you a statement that has in minus 2 and in, we're going to approach it slightly differently. Let's see. Let's start with part 1 though. Now, I1 is when I sub in 1 into cot. Guys, you can integrate cot, can you? Yeah. Now, first question for you. How do you integrate cot? Yeah. This is one of those ones where my students get a bit confused because they're like, oh, cot, it's not a standard integral. Cot, like tan, you break it up. Yeah, break it up into cos on sine. And then we apply that rule where if the derivative of a fraction is on top, then I can use ln, right? So this is just ln because we know that if this guy here was a function, then the derivative sign is this guy, right? That's f dash x. Yeah, so then I know this guy would be ln of sine x, the function itself downstairs, plus c in this case. The limits part 4, 6. Now what's that? ln sine pi 4 minus ln sine pi 6 ln root 2 on 2 minus ln half. So combine the logs, that'd be ln root 2, which goes using a log, that's para half, so then half ln 2. Boom. That's 1 mark. Wow. Okay, a bit long-winded for 1 mark. Man, that's unfair. 2009, okay, Sydney grammar, thanks. Part 2. I guess it's 1 mark because it's not difficult. It was just tedious, right? It just took a bit of work. Now, this one here. I say this to my students. A lot of times when you do recurrence, we do the traditional way where we try to split it in by parts. When it's just in. When they give you an expression where they go in minus 2 plus in, right? My advice would be to firstly put in the integral version there. So go pi on 6, pi on 4, cot n minus 2 dx minus, that's a bad n, that's n, and then integral pi on 6, pi on 4, cot nx. Since we share a common limit, we can combine the integral, right? So let's go there. Now I have no idea how much space I have. I probably need to start a new slide, but let's persevere. N minus 2 dx minus cot nx dx. All right, guys. Now, once you're here, right? What do you do next? Oh, no, right, I have no space. So copy that. Let's go here. delete, delete. Let's move this up here. Oh, that's not moving it at all. That's resizing. Okay, let's move this up here. Give me a lot more vertical space. All right. So from here, the technique is actually quite straightforward. I'm going to factorize this to make it simpler. But in fact, what I'm going to do is I'm going to force factorize, right, the cutout. Let's see, is that what I want to do? Let's see. Yep. Force factorize cutout and cut in x. Now, in this case, what did I do? I actually did it wrong. That's a plus. Cool. That from the cot x, when I force factorize, that's 1. Now, when I force this guy out, it will be cot -2, right? X here, when I force it out on dx. Why am I doing that, by the way? Because I want to get, now, what is that? Because cot is the reciprocal of tan, and so then -2 is the reciprocal of, sorry, cot is the reciprocal of tan, and that's the reciprocal of cot, so that must be tan, right? So that's pi on 6, pi on 4, right? So I'm going to use my big brain strategies here. And also, actually, let's do it. I'll do the bracket first, right? Just to illustrate what I'm trying to do. I'm going to replace that with tan squared x, right? Because reciprocal, right? So that becomes tan squared x plus 1. Now, before I move on, guys, tan squared x plus 1, what's that? Sec squared. Sec squared. Sec squared is important because the derivative of tan is sec squared, because the integral of sec squared is tan, right? Derivative of tan is sec squared. So if I use the substitution method, it'd be nice if I had an expression in terms of tan. Oh, wait a second. I can repackage this guy in terms of tan, can't I? Because that guy there would equal to tan x to the power -n, right? Yeah. So why am I doing all this? Actually, I'll do it later. Now let me just still write that as cot nx, because then I'm going to do a double sub now. I'm going to replace this guy with this. I'm going to replace this guy with sec squared. I'm doing this because it gives me an expression where I can use the substitution method, or just, the reverse chain rule method, right? That, where if that's tan minus nx right now, that's multiplied now by sec squared x dx, right? If tan x is my function, that's my derivative, guys. I then add 1 to the power, right? So then I go, that then equals to tan minus 1 plus 1, add 1 to the power, yeah, divide by that new power, take that to the limits of pi on 4, pi on 6. Yeah, because that's the derivative, right? So for example, this guy here was fx to the power of minus n, that is f dash x, right? So I can do all that. Now, I'm hoping that, guys, where this is going to take me, once I sub in the limits, I can get what I want. So can I jump over here so I can have a little bit more white space? That guy there, I'll bring that power out. Let me just check my math. Cool, that looks fine. Minus n plus 1. Right, then sub in pi on 4. So that's 10 pi on 4 to the power of minus n plus 1 minus 10 pi on 6 minus n plus 1. Okay, now looks like I'm going to have to do some nasty work here. I think that's 1. That's not nasty at all. That one is. That's 1 on root 3. All right, what have we got here? What do I have to prove, guys? N minus 1. You know what? It feels like I'm going to force factorize the negative out here. So I get minus n minus 1. Hopefully that gives me something, right? So that's definitely 1, no matter what you do. Yeah, and here what I have, I got 1 on root 3, like pi, yeah, pi 6 is 1 on root 3. And that's, now I'm gonna take it to a negative. I'll factorize the power, factorize negative out. Right, everything's here, makes sense because look at this negative, right? And this order swaps around. And then this negative and this reciprocal swaps around. And I have essentially, I'm almost there, right? Almost there to get 1 on n minus 1. Swap the order around, bring it upstairs. So that's root 3. And, oh, sorry, n minus 1 in the bracket. Good, good, good. N minus 1, minus 1. Guys, para half. Multiply it out, therefore. Therefore, in minus 2 plus in equals to 1 on n minus 1. 3 to the power of n minus 1 on 2 minus 1. Damn, that was a little bit intense, right? Certainly wasn't your usual recurrence though, but hopefully that was all right. Guys, recurrence with trigonometry. That's how you do it. Sine and cos questions. Take out one lot of sine or one lot of cos so you can integrate. Sec and cot, take out, oh sorry, sec and tan, you take out 2 lots because you can integrate. Now, if it was tan, which I didn't do here, if it was tan, you take out tan squared because then you can repackage tan squared as sec squared minus 1 to integrate. Guys, hopefully that was a useful video. I've got one more video in the series to do with sort of more difficult questions and just different in general. Hope you liked the video. If you did, give me a like, subscribe, tell your friends. I'll see you guys in the next video. Cheers.